Welcome back, everyone. We're going to continue our journey of evaluating more and more complicated integrals, this time using more of the power of trigonometry. So, in particular, we're going to do some substitutions with trig functions. So the idea is, suppose that you have some sort of a nasty square root, right? Like in this first example, a square root of a squared. So here a is just a number. So this would be like 9. So that would be the same as, of course, 3 squared, right? So you have some sort of number squared minus x squared, but all that under some square root, which makes evaluating the integral maybe really difficult. So you try to play with it and nothing obvious happens, and so great, we're down to trying to use the power of trig to deal with this integral. Because the really cool thing about trig functions, they're also intertangled with each other through all these various identities. So we can do something really cool. If we had an integral that had a square root of a number squared minus x squared in it, we could substitute that number a times sine of theta into the x, right? And then magic happens. So let me show you what happens. We have the square root of a squared minus x squared. When we stick a sine theta in there where the x was, okay, well, now writing it out, maybe your eye starts to pick up what happens with the a. I've got an a squared, then I'll have another a squared when I square the a sine theta. So I could factor that a squared out, right? Which is a good thing because factoring that out under a square root, oh, maybe we see where this is going to go. When I factor out the a squared, I'll end up with an a squared times, big parentheses, 1 minus sine squared theta. Okay, so how does that help us? Well, if we think about our trig identities, well, sine squared plus cosine squared, that's 1. So if I switched it around a little bit, 1 minus sine squared, that's the same as cosine squared. So that lets us now take the square root of both the a squared and the cosine squared, and we end up with just a cosine theta. So that whole square root that was hard to deal with maybe, and we had a problem in an integral, we'll see lots of examples of this in a second, where we couldn't actually solve it because it was an ugly square root and the algebra wouldn't work nice because this was all underneath a square root. The whole square root thing just became a cosine theta, which maybe, we hope, when we do these problems, will be easy and we'll be able to integrate what's left over with all these just trig functions in it. So there's a couple other square roots that we can play the same game with. Suppose that we had a square root with an x squared plus a squared underneath. Well, then if we substitute x equal a tangent theta, then the same kind of trigonomagic happens, and we can use the identity that says that 1 plus tangent squared is secant squared, and that whole square root, just like the last one did, will turn into just a trig function, in this case, a secant theta. And if we had the square root of x squared minus a squared, well, again, if we substitute in a secant theta this time, 1 minus secant squared is tangent squared. That's the root of how we would turn that ugly square root into just a tangent theta. So again, normally I don't encourage people to memorize a bunch of formulas, except those, of course, those integral rules from the beginning and derivative rules and trig rules. But all through the earlier stuff we were doing, when we were solving word problems, I was saying, don't try to memorize the formula out of the book, just draw the picture, right? Well, here's an example of a place where we really just are better off memorizing things. So this table is something you'll want to have memorized. You'll want to know that if you have, say, a square root of x squared plus a squared, right, that's just screaming out for trig substitution with x equal a tangent theta, and that whole square root, the entire square root, trigonomagically becomes just a single trig function. That's really cool because it lets us turn square roots that are hard to deal with algebra into just one single trig function, which hopefully will be easy to integrate. Okay, this desperately needs an example, right? So here's one with a square root of x squared plus 4 in the denominator, right? And what are we going to do with it? Well, I mean, there's nothing that looks obvious that we already know how to handle this. No substitution, integration by parts would be ugly. I mean, there's nothing here that's nice. So it's just, screaming out, hey, I'm a square root. I've got an x squared plus 4 inside. That looks like my formula, right? X squared plus a squared under the square root. Now, what would my a be? Well, if the a squared is supposed to be a 4, of course the a will just be 2. So this is an example where I have a square root of x squared plus 2 squared. So I let x equal 2 tangent theta. That will fit what we had in our chart a few minutes ago, and that whole square root will become 2 secant theta. Okay? But before I do that, there's one other bit of this integral I'll have to worry about. What I just said, the trigonomagic will turn that square root into 2 secant theta, but there's still a dx up here. And if I'm going to have an integral with thetas, I need to do something about that dx and turn that into a d theta. And the way we do that is just take the derivative and set things up with dx's and d thetas. So if x is 2 tangent theta, when I take the derivative, dx will be 2 secant squared theta d theta. Of course, the derivative of tangent is secant squared. So now this is not quite the same as u substitution. With u substitution, we're kind of doing it backwards, right? We let u equal stuff with x's. Here I'm letting x equal stuff with thetas. So it's actually a lot easier because the square root just becomes 2 secant theta, and the dx, I don't have to try to make up a du and work so hard the way when I do u substitution, trying to put things inside the integral and divide things outside the integral. This just works. Dx is 2 secant squared theta, right, d theta, and so it just works. Okay. And what's even better is the 2's cancel, of course, and this secant in the denominator cancels with one of the secants there, so this whole thing just becomes an integral of secant theta. That's really, really cool, and that's what we'd like to have happen with these sort of integrals. We'd like to be able to do a trig substitution that turns this ugly integral with a square root in it into something that's really easy. So suddenly the magic of the trig functions, stuff cancels, stuff has identities, stuff just becomes really easy. So if you remember back from our list of integral rules, the integral of secant and tangent, lots of other things were just formulas from that sheet. And the integral of secant's one we should know. And hopefully everybody remembers. If you don't, then this is where you have to know it. The integral of secant is the log of absolute value of secant plus tangent. Okay? And then, of course, we tack on the plus c. And you think, great, I'm done, except I'm not quite done yet. Because remember, the original integral was full of x's. And now I've got an integral full of thetas. Just like when we do u substitution, we have to go back and plug the x's back in. We'll have to go in here and plug the x's back in. And that's actually a little bit more of a wrinkle than it is with u substitution. The actual substitution, when we do trig substitution, is easier. The substituting backwards is the harder part. Here's why. Right? Figuring out what tangent of theta is, that's not too bad. I mean, I can just solve my original equation there. If x were 2 tangent theta, just take the 2 to the other side, and x over 2 is tangent of theta. So I can just plug in the x over 2 right there where the tangent theta is, and I'm good to go. The problem is this secant theta. I don't really know, right, how to untangle that to make that into a bunch of x's. Well, or do I? Well, if you remember back in Cal 1, we actually, in the review section, covered the trick that you need here. The problem is we do this in Cal 1, and of course everybody forgets it by the time they get to Calculus 2. So here's how we make this work. We're going to actually draw a triangle with the angle theta in my triangle. And I'll label the sides of the triangle, and we'll be able to just read off the various trig functions. So here's my triangle. I'm going to draw this triangle with this angle down here in the left side corner there as theta. So that angle there is my theta. Okay? And I'll label the sides so that that's the right theta. In other words, if tangent of theta is supposed to be x over 2, well, Tangent is opposite over hypotenuse, so the opposite side should be an x, and sorry, what did I say? Opposite over hypotenuse? Opposite over adjacent. The tangent of theta is opposite over the adjacent, so the opposite side should be x, and the adjacent side should be 2. And if I label my triangle that way, then my angle theta, right here in the corner, right, is the right theta, because its tangent is x over 2. That's perfect. So I can just use this now to read off my various trig functions. Or I could if I had the hypotenuse side labeled, right? Then I would know all three sides of the triangle, and whatever trig function I want, I could just read off from the triangle because I know it's whatever side divided by whatever other side. And this isn't hard either, because what's the hypotenuse? Well, this is where the Pythagorean theorem rides to the rescue, right? All of this trig stuff really comes down to the Pythagorean theorem most of the time. So what we know is that the hypotenuse squared is equal to, well, x squared plus 2 squared. So if I take the square root of both sides, then my hypotenuse becomes the square root of x squared plus 2 squared, or x squared plus 4. Now, you may notice that x squared plus 4 is colored blue here on the screen, and that's because it's supposed to remind us of the original square root of x squared plus 4 that was in the original integral when we very first started this problem a few minutes ago. And that's what should always happen. If we've done this problem correctly, the missing side that we use the Pythagorean theorem here to fill in will always be that original square root we started with. So if it doesn't work out that way, it means I've labeled my triangle wrong somehow. Okay? So the missing side of the triangle should always be the original square root we started with. Now, I just read off the various angles and we're good to go. So what's the secant of theta? Right? That's the first thing I need to fill in here. Right? Secant of theta. Well, that's going to be hypotenuse over adjacent. Or if you're not used to thinking about secants, I always have to say secant is the reciprocal of cosine. Cosine would be adjacent over hypotenuse. So the reciprocal would be hypotenuse over adjacent. So secant theta would be the square root of x squared plus 4 over 2. And of course the tangent, we knew that one to start with. That was opposite over adjacent, the x over 2. So that lets us substitute our x's back in for thetas. We had to do a little trigonometry to do it, but that's not too bad because that's the power of the trig, right? Okay, let's do another example. So here's another integral. It has a square root of 16 minus x squared in the denominator. So that means our a will be 4 because we'll treat the 16 as 4 squared. There's an x in the top and a dx in the top. So we'll have to substitute in some stuff when we get to that point. But to deal with the square root, we look at it really closely and we go, okay, that's a square root of a squared minus x squared. So I need to know which of the integrals from or which of the substitutions from my original table do I need, and let's flip back to that table. So it's a squared minus x squared. That's the first one on the table, right? So it's the one with a square root of a squared minus x squared, which means I need to let x equal a sine theta, and the whole thing becomes a cosine theta. Okay. If you have trouble remembering these, and sometimes people do, think about the derivatives of the inverse trig functions. That's really what's going on here. The derivative of inverse sine has a square root of 1 minus x squared in it. The derivative of inverse tangent has an x squared plus 1 in it. The derivative of inverse secant has an x and then a square root of x squared minus 1. So if you remember those derivatives of the inverse trig functions, that will be a big hint as to which of these works and help you memorize the table that we need. So we go back here, we'll let, according to our table, x equals 4 sine theta. Okay, that's great. We need to do something with the dx, so the derivative of 4 sine theta would be 4 cosine theta with the d theta. So I can start substituting stuff in now. The square root from our trigonomagic, by doing the substitution we're doing, that whole square root becomes 4 cosine theta. There's an x on top that we'll have to deal with. So that x, well, we know what x is. It's 4 sine theta. Right? So this 4 sine theta becomes the 4 sine theta in the numerator. Then we know what dx is. It's 4 cosine theta d theta. So I plug that in. So there's actually 3 things I have to deal with substituting. The square root, that becomes 4 cosine theta. The x, well, it was 4 sine theta. We just plug that in. And the dx becomes 4 cosine theta d theta because I took the derivative of x. Now again, magic happens, right? All kinds of things are canceling here. We're left with just 4 sine theta because the 4 cosine thetas cancel. And that's super easy to integrate. If we integrate 4 sine theta, we get negative 4 cosine theta. And again, whenever I integrate a sine or cosine, I have to stop and ask myself, because I haven't memorized the other way. The derivative of cosine is negative sine. So yes, I'll need a minus sign in front of this. So when I integrate 4 sine theta, I get negative 4 cosine theta plus my c. So awesome, right? We're almost done except for turning the thetas back into x's. And that we can do by drawing our triangle. Here we go again. So if x were equal to 4 sine theta, then I can figure out what sine theta is and how to label my triangle, because sine of theta would be x divided by 4. If I take that 4 to the other side, x over 4 is sine theta. Now, the sine is the opposite over the hypotenuse. So that means that the opposite over hypotenuse should be x over 4. That means I label the opposite side as an x, the hypotenuse side as a 4. I just read that off of my fraction. Okay? Now, I've got a missing side, but I can find that from the Pythagorean theorem because I know that the hypotenuse squared, the 4, plus the opposite side squared, plus the adjacent side squared, right? Well, wait a minute. Let me say it more carefully. The hypotenuse squared should be the opposite side squared plus the adjacent side squared. I'm missing the adjacent side, so the hypotenuse squared is going to be 16. Subtract the x squared, and then take the square root, and that should tell me that my adjacent side should be square root of 16 minus x squared. And again, that missing side in my triangle should always be the original square root we started with. And sure enough, it is. There's my square root of 16 minus x squared. And now I just read off my answer because I need to find the cosine of theta right there. And the cosine is adjacent over hypotenuse. So I will end up with negative 4 times, my screen freaked out on me, will be negative 4 times cosine of theta, which is square root of 16 over minus x squared over 4. Of course, I could go ahead and cancel the 4's, but I didn't on the screen because I wanted you to see where everything came from. Right? Now, it's probably worth pausing for just a second here because I hope maybe a few of you have looked at this integral and go, wait a minute, why is he doing all this trig substitution stuff? This is all complicated and long, and I know an easy way to do this integral. In fact, if you stare at that integral for a second, the original one there at the very top, anybody see an easy way to do that one? Yeah, this one could have been done with u substitution. You could have let u equal 16 minus x squared. Then the derivative of 16 minus x squared would be 2x dx. And sure enough, there's an x there. So we could have just jumped straight to doing this one with regular old u substitution. So why did I bother doing this one with trig substitution? Well, for 2 reasons. One is I wanted an example that I could show you, right, of how trig substitution works. But more importantly, it's really, really important as we get closer to thinking about doing these on an exam that you keep in mind there's often more than one way to skin an integral, right? This thing is sitting there and meowing at us, right, to push my cat metaphor. So there's more than one way to skin an integral. You very likely may have an integral in the exam that you could do more than one way. And so part of the challenge in the exam is to know the different ways you could evaluate an integral and be able to quickly figure out which is the one I really want to use. Okay? So in this example, it'd be perfectly okay to do trig substitution here, and on the exam you'd probably have time. But it's much quicker and easier for this case. You could just do u substitution and you'd be done. Let's try another one. So this one's a little more complicated because there's an x squared in the numerator, then our square root of 5 minus x squared in the denominator. Now, this is the square root of, oh wait a minute, that's a 5 minus x squared. So what do we do with that? Because remember, it's supposed to be square root of a squared minus x squared. And we would let x equal a sine theta. What's our a, right? Because that's a 5, not like a 16. When it was 16, you could let the a be 4, right? There was an obvious square there. Well, in this case, there is for this one too. It's just that we need to let the a be square root of 5. So in other words, we treat that 5 as being square root of 5 squared. Okay? So even though that 5 doesn't necessarily scream, hey, I'm a number squared, the way that 16 did, it's still okay because you can still treat that 5 as square root of 5 squared. Okay? So we let x equal square root of 5 sine theta. Okay? And of course, the dx will be square root of 5 cosine theta, d theta, and we proceed to substitute in stuff the way we did before. Our trigonomagic happens to that square root integral, a square root. And the whole square root of 5 minus x squared becomes square root of 5 cosine theta. Okay? The x squared on top becomes square root of 5 sine theta squared. Now that's really cool because the square root of 5 gets squared now. It's just a 5, and the sine squared is just sine squared. And then the derivative is square root of 5 cosine theta. We put that in there. And wow, this is really cool because stuff is canceling. The square root of 5's cancel, the cosines cancel, and I'm left with just a 5 sine squared theta d theta. That's great because that's an integral we know how to do, right? Again, the goal of all this is to start with a square root we didn't know how to deal with. Right? This one was not susceptible to substitution. There was nothing nice that I could have done with this original square root. But by turning it into a cosine theta and then changing all the other x's to what they had to be to match it, I have an integral that just has a 5 sine squared theta. And that's an integral we know how to do, right? Because how do we do sine squared? Well, there's a trig identity that says sine squared of theta is 1/2 1 minus cosine of 2 theta. Right? So we just do our trig identity that we've done before, and now I have a 5/2, right? The 5 from the original integral and the 1/2 from the trig identity. I pull that outside and then integrate. 1 gives me theta. When I integrate cosine of 2 theta, I get sine of 2 theta, but with a 1/2, because technically in that little step I'm doing one tiny bit of u substitution, but again, I'm doing it really fast, so I don't even write it down. So 1 minus cosine of 2 theta, when I integrate it, becomes theta minus 1/2 sine of 2 theta. Okay? All that's in parentheses with the 5/2 stuck way outside of that, plus our c. So awesome, right? All we have to do is our substituting back in. But there's one little wrinkle here that we have to be a little careful of. And this actually, maybe more than anything else in this whole section, throws people off because they want to do something crazy here, right? Because they see this sine of 2 theta and they think, yeah, I'll do it like I did all the other problems, and I'll just take that 2 right there and I'll just stick it somewhere. I don't know. I'll just stick it somewhere. and you can't just stick it somewhere, right? That's a 2 theta that we're taking the sine of, not a theta. In other words, if I try to draw my triangle and use my equation over here that sine of theta is x divided by square root of 5, I could draw that triangle. I could draw my angle, my theta, draw the sine, as x and square root of over square root of 5, labeling all my sides like we've done before. That'd be great, except the angle I've drawn is theta, right? And the angle I'm taking the sine of here is 2 theta. And I can't just ignore that and just stick the 2 somewhere else, right? That's not the same angle. If you don't believe it, think about what happens if you have like 45 degrees, like pi over 4. If you double that angle, you get 90 degrees, right? You get pi over 2. So and you think about what happens to sine, the sine doesn't just double or something, right? The angle doubled and the sine doesn't. It changes in really different ways. So we need another trig identity. And the trig identity that rides to the rescue here is one from our list of trig identities that we have to have memorized, and this is why it's on the list. Sine of 2 theta is 2 sine of theta times cosine of theta. That's really cool. That gives us something we can do now, and it's yet more trigonomagic, right? That the trig identities ride to the rescue here, and we can finish off the problem using using the trig identities to simplify what we had. In fact, even better, the 2 from the trig identity will cancel with that 1/2 that came from the integration by substitution that we did. So this is great. So we just draw out our integral now, or our triangle now. We know that sine of theta, again, sine of theta, not the 2 theta, but the sine of theta, is x over square root of 5. So that means the opposite side has to be x. The hypotenuse has to be square root of 5. The missing side should be the original square root. And sure enough, it is, right? Because if I take the hypotenuse and square it, I get 5 minus x squared. And then take the square root, that gives me the adjacent side. That's the square root I started with. That's the missing side. Everything's looking great. Now I can just start filling in the rest of the substitution here. Well, okay, one little wrinkle. There's a theta. What am I going to do with theta? Because if it were sine of theta or cosine theta or cosecant of theta or any trig function, I could read that off my triangle. But here it's just a theta. Well, there's only one thing I can do with just a theta. I'm going to call that theta inverse sine. Right? So if you remember our original substitution over here, x was square root of 5 sine theta. If I take the square root of 5 to the other side, I get x over square root of 5 is sine theta. So all I can do to simplify this to tell me theta is to call theta inverse sine of x over square root of 5. So that's actually not so bad because this integral may have actually come from an inverse sine, and so that that you'd expect that to happen. That maybe an inverse sine might show up in your answer occasionally. Now for the 1/2 and the 2 cancels there in the brown part, and I can read off the sine, that's x over square root of 5, and the cosine, which is square root of 5 minus x squared over square root of 5. Okay, and then we add on the plus c. So, wow, a lot of work, right? And another couple of new trig identities. But this was really cool that the trig just sort of shows up, waves its magic trigonometry wand at it, and everything, works out really cool in ways that it couldn't have if we were just doing just straight algebra. One more quick note about the way I've written this answer. On the exams, and as far as the web work homework goes, and in even the homework that you do on paper, it shouldn't matter whether you simplify it or not. I don't care on the exam if you bother to simplify this. For example, you see the 2 square root of 5s in that denominator. You could go ahead and multiply them together and get a 5. And in fact, that 5 would cancel with the 5 in the numerator outside the parentheses. You could do a whole bunch of algebra and simplifying stuff. I actually really don't care whether you do it or not because two reasons. One is people sometimes will do a bunch of algebra to simplify their answer, do it wrong, and then I have to take off a point because they did some crazy algebra simplifying, and I'd rather you just not do it at all rather than risk doing it wrong. But also, the point here is being able to do the integration, not doing the algebra. So, I'm not testing your algebra skills, I'm testing your integration skills. At least the only part of your algebra skills I'm testing are the ones that you need to get to the point we have here. In other words, the only algebra I'm really testing is the part that you need to be able to evaluate the integral. Once the integral is evaluated, then doing some more algebra to it doesn't really, gain us anything. Okay, one more quick example. This is something you may have forgotten, or lots of people, I think, deliberately blot out of their mind. if you have a square root that looks a little different, this is a square root of x squared plus 3x minus 5. We can still do this, but we need to do a little bit of algebra before we do a lot of trig. So the problem is that 3x, right? If the 3x weren't there, I'd have x squared minus 5, and I'd just proceed with my business. So I need to do something to get rid of that 3x. And the thing that I do is complete the square. So everybody hates completing the square usually, and it's usually, if we were in a face-to-face live class, it'd be a collective, oh, right. so if you didn't do it, everybody do it with me. Oh, okay. So how do we complete the square? Well, remember what we do is we take that -5, we move it over to the side. We take the the 3, the coefficient of the x, cut it in half, so it gives us 3 halves. Now we square it. Okay, that will give us 9/4, and we add that inside the parentheses. That will make what's in the parentheses a perfect square. But now I've added 9/4 in the parentheses, so to keep things from being changed, I have to subtract 9/4 outside the parentheses. Okay? Then, of course, what happens is the parentheses, it's now a perfect square. It's x plus 3 halves squared. If you don't quite believe that, or if it's been a while since you've thought about completing the square, FOIL that out, right? So you would get x squared plus 3x plus the 3 halves squared, which is 9/4. So that makes the whole parentheses there into 1 something squared. Then the -5 minus 9/4, that becomes -29/4 when we do a little arithmetic with some fractions. Now we have a square root with something squared minus a number. That's the kind of thing that looks like it's susceptible to trig substitution. So here's an example now. Suppose I had this integral of 1 over square root of x squared plus 3x minus 5. Like we saw on the last screen, the trick is to do completing the square, and we turn this into a purple x plus 3 halves all squared minus 29/4. That's all underneath my square root. So this doesn't look exactly like what we were doing before, but it will if I do one step of u substitution first. Let's let u be the x plus 3 halves that's in the parentheses. So I take that stuff that's being squared there in the parentheses, make that my u. Of course, this is easy because du will be dx, so the substitution goes really quick. And I get 1 over the square root of u squared minus 29/4. Okay? And then a du on the outside because the du and the dx were the same in this case. So now that's an integral that's sitting there waving its hands at us going, hello, trig substitute me. I'm ready to go. Let's do trig substitution. So we will. Right? So here's the integral from the last go round. We have 1 over square root of u squared minus 29/4 du. So instead of using x for our variable, we'll be using u's. But for the most part, this is just like the trig substitution problems we've already done. So if we look at this, there's the u squared minus a squared. Of course, the a will have to be square root of 29 over 4, which is an ugly number, but it's just a number, and we just carry it along with us. So if we think back to our table and our substitutions, what we need to do is let u equal a secant theta. Okay? So if we do that, the du will become a secant theta tangent theta, d theta, because of course the derivative of secant is secant tangent. We use our trigonomagic to turn that original ugly blue square root into a tangent theta. And the du becomes a secant theta tangent theta d theta. Wow, okay, that looks like a lot of messy trig, but you see the really cool thing is most of this stuff cancels. The a's with this ugly square root of 29 over 4, that cancels. The tangents cancel, and I'm left with just the integral of secant theta d theta. So all of this sort of messiness is really easy because of the trigonometry, right? Everything cancels nicely. We're down with just an integral of secant theta, which I know how to integrate secant theta. That's log of secant theta plus tangent theta, with, of course, the absolute values around that, plus our c. Don't forget the c. Now, all we have to do is resubstitute things back in, and that's not hard either. We can draw our triangle. The numbers are a little uglier because we have this square root of 29 over 4, but it's not too bad. So if I look at my original u equals right here, u is square root of 29 over 4 secant theta. So if I take the square root to the other side, secant theta is u over the square root of 29 over 4. So how does secant work? Secant is hypotenuse over the adjacent. Or if you don't like that, it's the reciprocal of cosine, and cosine is adjacent over hypotenuse. So either way you want to think about it, we put u in there as the hypotenuse, and the square root of 29 over 4 in there as the adjacent side. And if we've done all this correctly, the missing side should be the original square root we started with. And sure enough it is, because I need to take the hypotenuse squared, right? That's my u. And u squared minus the square root of 29 over 4 squared, and take the square root to get the opposite side. And then just read off the answer, right? So the secant, that's the hypotenuse over the adjacent, so u over square root of 29 over 4. Tangent, that's the opposite side, that's the square root of u minus u squared minus 29 over 4, all divided by the adjacent side, which is square root of 29 over 4. Wow, that's ugly looking, right? It's just really, really hideous, but it's not hard, right? It's just a matter of writing down square root of 29 over 4 instead of just, 4 everywhere. But it's just a number. So it looks awful, but it's no harder than what we've been doing. It's just that the number is just a little uglier. And of course, you won't have a calculator when you take this on the exam. And so square root of 29 over 4, it's just square root of 29 over 4, right? We just leave it in the problem and square root of 29 over 4, that's what it is. And we just leave it like that. I mean, if you really, really want to get creative and take the square root of the 2 of the 4 and make it 2. In other words, make it square root of 29 all divided by a 2. Okay, fine. But it's still just a number, right? So it's an ugly number, and we just leave it in there and let it be ugly. That's just what it does. But of course, we're not quite done yet. Because remember, the original problem had x's in it. We did u substitution, then we did trig substitution. So the very last step is we have to remember that we have to substitute back in for x's. So the u was way back a couple screens ago, x plus 3 halves. So everywhere there's a u, I turn that into x plus 3 halves. And that's easy enough, right? Now, one more quick word about algebra and simplifying and stuff here. This is actually how I prefer you write your answer. This makes it really easy for me on an exam to look at it and tell, oh, okay, they did this side divided by this side and so on. It's really easy to grade. But if you were to plug this into, say, Wolfram Alpha, you don't get anything that looks like this at all, because they will always go through and do a bunch of algebra. In fact, in the answers in the back of the textbook, they do a bunch of algebra. And in particular, the kind of algebra that they'll do, they will take these two fractions, because they have the same denominator, and put them together. Well, okay, that's not so bad. But then they will use log laws to say it's the log of the numerator, right, minus the log of the denominator. And notice that's just a number. And so very often they'll take that number, put it with the c that's on the outside and say, hey, log of square root of 29 over 4 plus c, well, it's still just a number, and the c is just a placeholder for some number. So a lot of times when you see this, if you put this in a calculator or put this in Wolfram Alpha, that square root of 29 over 4 won't show up in the answer. And the reason is they've just folded it into the c after they did a bunch of algebra. I'd much prefer you leave it like it is. In fact, if you suddenly show up with answers that look like they came from a calculator and not answers that look like they came from actually working the problem, that really starts to set off alarm bells going, hey, where did they actually get that answer there? Right? So if you don't have the work to support the answer, there's just a bunch of nothingness, right? Scribbles and such. And then suddenly the right answer appears in a form the calculator would give you, as opposed to a form that you'd get if you actually worked the question out using trig substitution the way we have here. That starts to look suspicious and looks like the sort of thing that gets turned in for discipline issues. So don't do that.